So, as you saw in the opening slide, they were doing graphing exponentials, graphing logarithmic, and exponential and logarithmic functions. We're going to be dealing with some operations, combining the functions, similar to the function notation that we used back in the Introduction to Functions lesson back in Term 1. So, I'm not going to spend too much time on the exponential functions because I know a lot of you have already done this work. And also the alternate assignment that's on the message boards for this particular assignment, Mrs. Gray has a step-by-step tutorial that she made. Isn't that right, Mrs. Gray? I'm pretty sure. So we're not going to spend too much time on that because I think what is going to be slightly more challenging is when we deal with some of the combining. I know I had a couple students contact me last week about some confusion in certain parts of the lesson, so I'll try to go over that. I think is Emily here? Let me look. Yes, she is. Yes, Emily was one of them. Devin, I believe, sent me a question about domain and range, so I'm going to take some time to explain that in a little more detail as well. So exponential functions. So all we need to look for when we're saying, okay, well, is this an exponential function or not, is we just look for where the variable is. If the variable is in the exponent, then it's an exponential function. Okay, and you can see I've done some different things here. One thing that's interesting about the exponential functions, and this is important because it'll be on your Socrative quiz when we end the lesson. The base cannot equal 1. The reason the base can't equal 1 is because if we take 1 squared, 1 cubed, 1 to the 4th, 1 to the 5th, it would just always equal 1. So you would just always have a horizontal line, y equals 1. So the base can never be 1. The base can never be negative. So the only bases we're going to have is between 0 and 1, and then greater than 1. So it can't be 0, can't be 1. It could be anything in between those. Those are basically means it could be a ton of different fractions, an infinite amount of fractions, as a matter of fact. But typically we'll be dealing with fairly normal fractions, such as 1/3 I have in the example there, g of x. And besides what you need from the tutorial, Mrs. Gray made an excellent tutorial for the alternate assignment that you'll be doing for this actual assessment when you get to it. I'm just going to be showing you how to enter these in GeoGebra. There's some pretty important things like on the h of x there. You have to make sure that your actual variable, this is a quantity that's in the actual place of the variable, so that does need to be in parentheses. And notice I've written them horizontally here for you as well. So you'll enter them into GeoGebra exactly like I have them here. The reason I called them f of x, g of x, and h of x instead of all of them just f of x is so we can put all three functions up there at the same time. And we'll be able to take a look at some of the differences and also discuss exactly what we look for when we're determining the domain and range. Now, I'm going to go ahead and share GeoGebra with you, and I'm going to share it with you in the context is this is how your GeoGebra typically opens by default. I know I've shown you this before, those of you that were with us last term, but it comes up like this, which is not really the best way. Sometimes there'll be a little menu over here when you initially open it as well. I like to right-click in any blank quadrant there and then go and select grid so I have my grid lines. And then I'm just going to resize it here a bit just to make it proportionate. And notice my x and y axes are a bit off, so I'm going to kind of center that as well. All right, so I'm down here in the input bar. Now, those of you that are on a very small screen will probably actually need to maybe scroll down a bit, but just make sure you can see exactly what I'm putting in the input bar. So I put f of x equals, and it's 3 to the power of x. Just use my caret key, and then I'm going to hit enter. I'm going to go ahead and change the way some of these look so it's a little easier to look at them. We'll make this one green. Green's one of my favorite colors, so I'm going to make it a little thicker line there too. All right, so notice here, now it's going to write it just 3, and then the x on the exponent. It doesn't write the caret for us, so keep in mind that there's some differences there that you have to recognize as far as the way you have to enter things in to graphing technology horizontally. By the way, this applies to, if you're using Desmos, if you're using a TI-83, TI-84, it's very specific about the way you have to enter these values in to the graphing software, graphing calculator. Okay. So g of x, and this one I'm going to put my fraction base in parentheses as well. So in this one, I'm just going to use 1/3 as the base. I'm going to raise that to the power of x. Hit enter. And you notice that that appears to be the inverse of 3 to the power of x, if we're reflecting it over the y-axis here. So let me change the color of that one as well. And let's say, well, there's a really cool purple color there. We'll go ahead and use the purple. All right. Interesting to note, of course, that we have inverses here. More importantly, the purple function with the fraction as the base, it's going to it's decreasing as we look at it left to right. And if you look at your exponential function with a base that's greater than 1, then that's increasing from left to right. So sometimes you'll have questions about the, what does the function look like when you graph this particular function? You say, well, in this green one, the 3 to the power of x, it's increasing left to right. It intersects the y-axis at 1. Okay. A lot of your exponential functions, you're going to see y-intercepts of 1 because x is the value of 0 at that point. Of course, anything to the power of 0, of course, is 1. All right. Now, let's see what happens when we have something like when we had the h of x function. That actually had a quantity that was up there in the exponent. So we're going to do h of x equals, by the way, I know I've mentioned it before, guys. When I put h and then open parenthesis x, it automatically puts the closing parenthesis there. So make sure you, of course, move outside of that closing parenthesis before you continue here. So we're going to do a base of 3. And we're going to do an exponent of x minus 2. So since that exponent is x minus 2, I've got to make sure that I have it in parentheses there. And I'll show you the difference as well when we do just to the power of x minus 2, and we don't use the parentheses. We're going to have a different function there, a different type of shift. So I'm going to go ahead and hit enter here. Now, this is relative to the f of x equals 3 to the power of x, and you'll notice all of the points here, if I look at the x value of 1 and my green function, it has a y value of 3. But it's shifted 2 spots to the right. Notice every point here, this 1 is a good clear point. We can see that's shifted 2 to the right. So this is something that's very similar to the shifts that we dealt with back when we were working with the quadratic functions and the way they shifted left and right and up and down. That brings me to the point where we talked about what would happen if we don't use the parentheses correctly in this exponential function where x minus 2 quantity was the exponent. Let's see what happens if we just do 3 to the power of x minus 2. Notice I did not use parentheses around the exponent there. And you're going to see that that is actually going to be a shift down 2 places. See, everything is down 2 places here. All right, now, to address the questions that I've received last week about how we find the domain and range. First thing you need to realize is the domain is just input or x values. The domain is all real numbers for all of these type of functions, okay? Now, let's talk about the range, and I'm going to kind of reduce these to just a few functions here, actually just two. All right. As far as the range is concerned, what I want to look at here, the range is the output or my y value, so I'm only looking for my possible y values. In this case of the green function, 3 to the power of x, I just look at what the y values are. Well, the y values are everything greater than 0. Okay, now down here for the 3 to the power of x minus 2, my range would be y is greater than -2. All of my y values are greater than -2. There's something very important that I wanted to show you here. Obviously, if we just look at these functions, it looks like as we go to the left here, that the line, let's look at the green one, for example, that the line just turns into the x-axis, when in fact, it never touches the x-axis at all. So it reminds me of that old math question that I don't remember what math teacher gave me this question, but you know, they have the example where there's a frog and he's jumping closer and closer to the wall, and he jumps half the remaining distance to the wall every time. So, for example, if he were 2 feet from the wall, he would jump 1 foot. Now he's 1 foot from the wall, so he jumps 6 inches, and he continues to cut that distance in half. Well, the truth is he would never actually touch the wall if he continued that, because there are infinite amount of fractal values that we would run into as we continue to get closer to the wall. Although to the human eye, it would appear that the frog would be touching the wall. So I'm going to zoom in here, and we're going to look at this x-axis. If we look from here, it looks like, well, at -5, it's definitely touching the x-axis, right? Well, when we zoom in, we'll have to zoom in quite a bit here, you can see that we actually are just a tiny, tiny, tiny bit off of the x-axis. So we actually never touch the x-axis, and you can zoom in down at -10,000. You'll have to zoom in quite a bit because it's extremely close there, but they actually never touch. That's why we say our range is y is greater than 0 for that green function. Okay. So I hope that clears up the questions about the domain and range that I had earlier. And if you do need additional clarification, Mrs. Gray and Mrs. Carmichael, I'm not sure which one is monitoring the chat. I'm assuming that we're maybe all monitoring it. But so, all right. Now, like I said, I don't want to spend a ton of time on this, but I did want to point out one question that you'll see on, I think it's on this list, I'm not 100% sure, but they might give you a table, and a table of points, which we're used to seeing at this point. Sometimes functions are, you know, set up as points in a table, and they're going to give you, for example, a lot of different functions, like maybe this j of x function would be an example, and they would have a point here at -3, -2, and then maybe at 0, -1, and some points not necessarily all on that line, but very close to it, and they just want you to find the best one. Well, you can plot points in here. So if I just put in the input bar, open parenthesis, 1, 1, I'm just putting an ordered pair and hit enter. I can actually plot all my points in GeoGebra. And then you can simply put the multiple choice answers in and see which function actually represents the plotted data from the table the best. So, all right. So moving on, we're going to look at some logarithms. Like I said, I'm not going to spend too much time on this because Mrs. Gray has a very thorough tutorial for you that's available on the message board. So that's exponential functions. And we could do those by hand too, guys. I guess if we think of f of x equals 3 to the power of x as an example, no matter how complex your functions get, you can always make a little x and y table. So if it's 3 to the power of x, so in other words, if I said -1, you'll have to remember your rules of exponents there, that would equal 1/3. So you could actually go through and plot, plug in some values and plot them out, and you'll actually be able to do the graph that way in case you're wondering how to graph them by hand if you do choose to do so. I think in college algebra you'll probably have to. All right, so logarithmic functions, and these get a little more complicated. Important thing to remember is they're the exact inverse of the functions that we were just graphing, the exponential functions, but they're not the inverse in the sense that it's a reflection over the x-axis or the y-axis. It's actually the inverse as in it's a reflection over the equation y equals x. It's just a diagonal line that goes right through the origin. So what do they use them for? Logarithmic functions, it's how they measure earthquakes. That's when you see in the seismograph, Richter scale. Measuring decibels. So logarithmic functions, most of you probably have an iPad or some type of music player. Well, the volume knob that we use on our car stereo or iPad or anything like that, that's actually based on logarithmic functions. Radioactive decay, as you know, we have nuclear power plants throughout the country, and they actually have to bury this stuff, nuclear waste, deep underground, and they need to know how long will it take that radioactive material to decay where it's no longer harmful. And so they use logarithmic functions for that. Anyone that's going to any type of engineering, it doesn't list computer engineering here, but you do use it in that as well. But electrical, mechanical engineering, and measuring pH, and that's one of your assignments. So, all right. So let's see what we have here. Some students asked, I think it was Willie that called me last week or the week before. I don't know. Some of you guys work so hard, and you're so far ahead. Makes me feel like I'm going over material some of you have covered. I know for a fact some of you have already done this assignment, for example, because I've already graded it. But Willie, I think, called, and we was working out, I think, changing something to exponential form, and he said, well, hey, there's no base listed here. So if you see this last bullet down here, log x, well, if it doesn't list a base, it's a base 10. That's called our common log. Natural log is base e, and Mrs. Gray and Mrs. Carmichael and myself were just discussing some of that. Natural log, that's where you see the ln instead of the log. And so we're going to show you some differences in that in GeoGebra as well. So remember, inverse of exponential function over y equals x. This is important because we're going to be doing algebraically finding inverses with these functions, just as we found inverses of linear functions and rational functions, all of these things. We're actually going to find inverses here as well. So if we're finding the inverse of a logarithmic function, we will end up with an exponential and vice versa. So that's important to know. Okay, let's see what's next here. All right, some cool functions for us to try here. All right, so let's get our GeoGebra out. I'm going to probably have you guys graph some of these in a bit too. So if you do have the GeoGebra, or I know some of you use other graphing calculators. Actually, I'd like to go ahead and let me leave this green function up here. We could use that one to find the inverse maybe. And that'll be cool to see if it actually comes out correct. All right, so different logs. Let's get the log base 4 of x and log x plus 3. I just wanted to make sure I'm going to graph the correct things here. I know a few of you will certainly tell me if I do not, which I appreciate. All right, so I think this is the one I'm just going to do. Let's just do the most basic that we can think of. I'm just going to do y equals log. Look at all these options that come up when I put log. All kind of things. I'm just going to write log, open parenthesis. I'm going to put x in the parentheses. So what I'm intending to tell the software is that I just want the common log, log base 10 of x. And I hit enter. And what you'll notice here is it graphed g of x equals ln, and then in parentheses x. So it actually graphed something different than what I intended to enter. Now this is in your lesson as well, so it's not you know, anything that you can't look at the lesson and find this out, but I want the log base 10, I don't want the natural log. So let's look at how we do that. And again, step by step in your lesson, this is in there. By the way, and be prepared for questions. I don't know if you have them on your assignment, but maybe on the final exam about the rate of change. Remember, they might say rate of change from any x value to another x value. You just find the y coordinate that corresponds and then use your slope formula. All right. So I just want you to be prepared in case they ask those type of questions. So let's say I want log base 10 of x. This is the way you're going to enter it. I'm going to go y equals log, and I'm going to open my parentheses, and I'm always going to enter base, comma, argument. Base, comma, argument. So if I want a base of 10, I'll specify that base of 10, put my comma, and then put my argument x. Okay? And what do you think? Is it going to be the same? Is it going to be different? Let's see. We got to hit enter and find out. They're actually a very different function, guys. So that's the reason I wanted to show you. You know, after I type it in and hit enter, I always want to look up here, make sure that I actually have what I entered. And I think, and Mrs. Gray might have mentioned this to me earlier in the email, I think older versions of GeoGebra used to give you the common log. Is that right, Mrs. Gray? I thought they gave you the common log before. Yeah, that's what I thought too. But now you do have to specify that base. Okay, so that could get confusing if maybe you're looking, if you're answering a multiple choice question that says which of the following graphs is a match for this particular logarithmic function. Make sure that you're focusing on having the correct base on those. All right, so we could do this with anything. Let me look back at the slide real quick. So log, this is base 10 of quantity x plus 3. This is log base 4 of x. So let's go ahead and see how we enter those. All right, so I want log base 4 of x. Let me remove this natural log here. Log base 4 of x. So I'm going to do y equals log, open parenthesis. Remember, it's always base, comma, argument. So log, if I want my base to be 4, I put 4, comma, x, close the parenthesis, enter. Interestingly enough, it's not very different, is it? But remember what I showed you when we zoom really far in on these things, we can have quite a bit of difference. You guys saw a lot with the, I think it was the exponential functions where they had some questions about you investing money and things of that nature. Well, once you actually get up to a large sum of money, these tiny, tiny decimal values from here to here actually start to amount to thousands of dollars and then tens of thousands of dollars and hundreds of thousands of dollars. When you think of the budget that our federal government deals with, for example, that's a large budget. So if you make one small rounding error in a decimal that's in the thousandths place, it could end up being millions of dollars. So although there are slight differences, these differences are very important. All right, now let's do that log base 10 of x plus 3. And I'm going to remove this log base 4 of x function because I want you to see something that happens when we do this other one with the same base 10. So y equals open parenthesis, oh sorry, I'm already messing it up here. So y equals log, open parenthesis, I want a base of 10, and I want an argument of x plus 3. This is another strange scenario because I don't have to put a parenthesis around my argument, by the way. In other words, the argument is a quantity, and I'm just entering x plus 3 there. Notice I don't put any spaces between anything either. So when we hit enter there, remember the value is inside the parentheses. Back when we did quadratics, if the value was inside of the parentheses, then the shift was the opposite of what the value appeared to be. So in this case, x plus 3 actually is shifting all of my values here over to the left by 3 spots. 2, 3, 1, 2, 3, 1, 2, 3. So just something else to keep in mind, you might be asked about shifts in these type of functions. So, all right, now this is where we're going to spend a little more of the lesson. It's also where I'm going to give you guys some questions to work on yourself, and I'll give you a couple minutes when we get to those. And it's the part, like I said, that I thought might be a little more challenging. And it's when we're combining the functions. So if you need a review of function notation, that's not what I'm doing here today, but on page 2 of the lesson, it goes thoroughly over all the function notation. That's all the f of x and g of x and all of that stuff, just the way we notate the functions. Another thing to be aware of, there's sometimes not a lot of simplification that can occur. So, in other words, still the order of operations, the rules of like terms are still going to apply here. So we can't, if we have 3 to the power of x and then 3 times x, those aren't like terms. We can't combine them. They don't have the same exponent. So, if they asked us to combine something like that, probably not a whole lot that we could do as far as simplification there. All right, so now I'll start you out with let's start out with something that's hopefully a little easier. So this is, by the way, guys, they go over some examples of combining some exponentials and combining some regular functions, and all that stuff's in the lesson. Like I said, I want to focus our time on the things that I notice students having more questions about and maybe running into a little bit of trouble with. So in this case, and please excuse my handwriting, but they're asking us here, f of x equals log base 7 of quantity x plus 4. And then g of x equals log base 7 of 4x. By the way, guys, this is a big difference here. Notice the argument in parentheses. These two are very different. Keep that in mind. In other words, in the f of x function that I list there, the x plus 4 being a quantity, being in parentheses, means the argument of the log is x plus 4. And the one that I've highlighted in the teal color there, the argument is x. And then we're adding a 4. So your shift would be much different. Remember the shifts we looked at in GeoGebra. One of these would shift to the left. One of these would shift up. So big difference there. Keep that in mind. All right, so let's go ahead and work these out. F of x plus g of x. Well, they're just wanting us to add here log base 7, quantity x plus 4, plus log base 7 of 4x. All right, so adding up some logs here. Remember, and a lot of these, like I said, there's not going to be a lot of simplification that you can do. But in this case, we have the properties of logs that we can follow. In other words, this one was adding. So we can actually use our properties of logs here. Properties of logs tell us we can combine these two logs into one log. When we're adding the logs, we simply multiply the arguments. So I can actually write this as log base 7 of 4x times x plus 4. And then you can actually simplify that. Brings me to another important point that you'll have when you're working on your actual assessment for this. I answered some questions last week as well about equivalent forms. So when we look at the multiple choice, all of these may have been in the multiple choice. In other words, multiple choice could have listed that is the final answer, that is the final answer, that is the final answer. So we need to recognize that all three of these are an equivalent form. They're all the same. They're just written different ways. So I would hope they would maybe leave that as the answer if they were going to bother simplifying it all, applying the properties of logs. But like I said, we need to be aware when we're looking at these multiple choice answers that sometimes there will be some differences, sometimes there won't be. So, all right, I'm not going to review properties of logs with you, but I do want you to try this one on your own. And it's dealing with the same functions. I'll rewrite these up here. So f of x equals log base 7 of quantity x plus 4. And then our g of x was just log base 7 of 4x. All right, so give you about, 2 minutes? You guys think you can work that in 2 minutes? So just try to see how much of the properties you can apply there and do your best, and I'll work right through it here in just a moment. I guess I should mention, go ahead and type your response in the box here. I'll open up the chat for you. I think that might be very close, Devin. Anybody else have that one somewhat simplified? And Devin's on to the right idea here as far as the way we do the property. Yeah, Willie, I know. I'm going to do work through this one as an example here. I want to give everybody a chance here. This is going to be one of the examples that maybe doesn't have as much simplification that's going to be possible. I see what you're thinking about there too. Yeah. All right, so let's go ahead and work it real quick. F of x of log base 7 quantity x plus 4 minus log base 7 of 4x. So same thing. We go back to our properties of logs. And remember, if we look at the multiple choice answers, this may be the answer they want. But in most cases, if you can apply properties, they're going to want these answers in the simplest form. Even though we've sometimes, discussed simplest form, and sometimes they maybe didn't simplify it all the way, but so we consider the simplest form, but we also have to consider these equivalent forms on these multiple choice type questions. So the operation of subtraction, as far as properties of logs is concerned, means that I divide the arguments. So log base 7. Now, and I think Devin had the idea, but I think you put the 4x on top. Is that right? I can't see the chat box while I'm actually writing on this. So, so you were right on the money there with using the division. So it's always, this is always my numerator, whatever comes first. So whatever is being subtracted, that's going to be my denominator. Just like that. So hopefully they don't ask you to use change of base formula with that one. That would kind of create that'd be a pretty wild calculator entry or GeoGebra entry if we had to enter that in. But it can be done. This takes a lot of parentheses to do that. So I also wanted to point out, and we'll have some other examples that you guys can work out here in a moment. I had to make a couple more points. So now, in the lesson, in this actual lesson that's called Exponential and Logarithmic Functions, they do go a little bit into the application, but it's always going to be, be something like this, where they'll say, oh, you have to subtract the two functions, and then you're just going to be entering in a value for the x. So I'm not going to go over examples of that, but I'm showing you the actual concept, what you would have to do as far as simplifying your expression. I know all of you are really good at plugging in, different inputs and getting your outputs, or plugging in your value for the domain to get your range. But keep in mind that you do want to, of course, go through those portions of the lesson. They don't really ask you any questions. I went through all the questions from the test bank that I could anyway, and you don't have any application questions on your assessment. So, all right. Keep in mind on your unit test and on your final exam, you may very well have those questions. So you do need to go through that portion of the lesson. That's just not something that I'm doing here. Now, what I'm going to spend the rest of the time on here, besides your exit quiz, is going to be the inverses, because this is what, based on the questions that I'm getting, this is what most students were having trouble with, was when we were getting to the inverses. So most of you remember how to work with the inverses and how to find the inverses, a very specific set of steps, and I'll kind of verbally go through them quickly here, and you can make notes of it if you need to, but it is something you definitely need to remember, is all those steps to find inverse, because those steps are always going to be the same. So in this case, it says f of x equals log base 2 of quantity x plus 6, and they want us to find the inverse, okay, when x equals 4. So the steps to find the inverse, and I know a lot of you know these, but I'm going to kind of go over them for some of you that maybe need a refresher. First thing I'm going to do is, instead of f of x, I'm going to change that to y. So y equals log base 2 of quantity x plus 6. So step 1. So even if this were on an essay question, I expect everyone is going to get step 1 perfect. So you just change f of x to y. Now this second step, everybody can do this with 100% accuracy. I'm going to switch x and y. All right. So here's probably where maybe it gets more complicated for a lot of you, because we have to have a lot of experience, I guess, with a lot of practice isolating variables, and you've got all these different things. How do we get rid of radicals? And in this case, it's wow, how we've got to get rid of a log here. So once we get to this point is where I start getting more questions. But there's a rule that I want you to remember. By the way, they're asking us to find the inverse of a logarithmic function. And remember, I told you earlier, it's important that you remember the inverse of a log is an exponential. The inverse of an exponential is a log. So we're going to go back and forth with both of those type of functions as we work through these. Now, if there were logs on both sides, in a lot of cases you could just cross your logs out and be doing property of logs and solving and things of that nature. But when we don't have a log on both sides, in most cases you're going to do what's called change to exponential form. Now, one cool thing about it is this is a log base 2. So that helps me remember, well, base 2. 2 is my base. Here's how you change to exponential. Base to the power of whatever's on the other side of the equal sign is equal to my argument. All right, so the base of 2 kind of draws a, in this case it was counterclockwise, but if we could easily write this log base 2 of y plus 6 equals x, and then it's going the other way. There's not something you can specifically remember about the rule. as far as is it going clockwise, counterclockwise, anything like that. But you can remember your change of base. Base is 2 to the power of x equals my argument. Just like that. 2 to the power of x equals y plus 6. Now, if we think back to our rules of what are the steps exactly to find my inverse, well, change f of x to y, swap your x and y, swap their places, and then you isolate the y. So I've still got a bit more to do here. I've got to subtract the 6 from each side. 2 to the power of x minus 6 equals y. Then some of you, if you want the variable that you solve for on the left, we can move it to the left and write it this way. So y equals 2 to the power of x minus 6. So that's my inverse. I did all of that work just to find the inverse, and I'm still not done with this particular question because we have to plug in the 4. I also want to point out again, huge difference here, and I'm going to write this in this highlighted area. This is how important this is. There's a big difference between 2 to the power of x minus 6 and 2 to the power of quantity x minus 6. We even graphed something similar to that earlier, so we can look at the difference. Right? So make sure that you're subtracting 6 from this actual power here. You're not subtracting 6 from the x and the exponent. Okay? They're not like terms. They can't be combined. You can't move the minus 6 up there to the exponent. But they wanted us to find, it's written right up here for us, the inverse when x is 4. So all I have to do now is plug in that 4 for the x. So y equals 2 to the power of 4 minus 6. 2 to the power of 4 is 16, right? So this just equals 10. All right. Now, probably they'll say, if it was a multiple choice question, for example, f to negative 1. This isn't an exponent, it's just a notation for inverse, but they'd probably write it like that for your final answer. Okay? Yeah, my z's look like this. Isn't that the worst thing ever, though? Ashley, when your math teacher writes 2's that look like z's. But, no, all my z's have a line through them. But thank you for mentioning that. Thank you, Willie. All right, let's see. You guys think you could try one of those yet? Or you want to see another example? Think you can try? Okay. Lay it on me. All right. Let's see here. I've got one for you guys to try over here, and then I'll work it out too afterwards. But let's see. So this is one. I didn't try to really put anything different in this than what you guys were than what I did on the last one, for example. So go ahead and, especially if you took notes, you'd probably be able to do that. Remember, step by step, remember your rules for the inverse. And you're going to find the inverse, and then you're going to plug the one in for x. Remember, it's a log, so the inverse of that is going to be an exponential. Let's do 2 minutes. If you want to, absolutely. Hold on. Let me put the timer up, and then I'll give you whiteboard privileges. Just put your answer, do your work on your paper, and then just write your answer up there on the whiteboard. Good suggestion, thank you. Or type your answer in the chat, either way. Wow. Who wrote the 5 on the board in green? Good job. I should have left the chat closed so now everybody can see all of your answers. I hope your answers are right. Let's find out. That was quick. I gave you guys 2 minutes and you're all done before even 1 minute. It is. You guys are awesome. That's true, Emily. Good point. I guess you could go and do, I don't know though. I don't know if you could even, I don't even know if Wolfram Alpha would get that. Because it's so hard to enter it in. Plus it might think that you mean take this log function to the power of -1. It'll be like 1 over log base 3 of x minus 2. So everybody's saying 5 here. Okay. Well, let's see. That's probably right. I haven't worked it out yet, to be honest with you. All right. What was the question? I'll need the question here. Let me get some blank real estate. Now I can write it on the. I'll just write it on the whiteboard. I've got my good pen tablet today that actually writes on this stuff. So, steps. I change y, the f of x to y. Remember, that's always the first step. Change f of x to y. First step when we're finding inverses. And then I'm going to swap places here. So I put my x where my y is. And I put my y where my x was. In this case, I'm going to change to exponential to get rid of my log. So it's going to be 3 to the power of x equals y minus 2. And then what do they want me to plug in? Just the 1 for the x. 3 to the power 1 equals y minus 2. 3 to the power 1 is 3. I'm just going to add 2 to each side. So y equals 5. Just like that. So good. Wow. That's impressive, you guys, really. I was trying to have all this extra time near the end of the lesson, you know, almost an entire third of the lesson to focus on this stuff, and then you guys are like, oh, yeah, we can do that in 45 seconds. So, all right. Good job. All right, now let's do one. Let me go the other way here. I'm going to go from, let's see what we have here. Let's do this. This one's cool. So this one is, we're going to go from the exponential, but we're finding the inverse. And remember that the inverse, I'm saying this like, 20 times during this lesson. I'm not trying to give you any hints or anything like that, but it might show up on your exit quiz, just saying. All right. So they want us to find the inverse here. When x equals 4. So let's go through it step by step here. When I was originally learning logs, I thought, wow, these are really hard. It takes a lot of practice to get comfortable with them. All right, so step 1, change f of x to y. Then swap my x and y. I guess I should... Actually, I guess I'll have to come up with questions without 2's in them for you. How about this? Let me try this. Is that a better 2? Still looks kind of like a z to me. Anyway, so x equals 2 times 4 to the power of y. Now, we have to get the y by itself. And these bases are definitely not the same. So this is going to be a handful to get the y by itself. probably, right? Well, that's what we have logarithms for. We can take the log of each side here, but you don't want to take the log of each side just yet. We want to get rid of this 2 first. So I'm going to have to divide each side by 2. See, the 2 is not to the power of y. Only the base 4 is to the power of y. So let's get everything away from that base before we try to isolate that y. So now I've got x over 2 equals 4 to the power of y. Everybody following so far? Like I said, I think this is probably harder going from expo to log than the other way around. But anyway, so we have to, at this point, take log of each side. Now, here's what's cool, and this is a very, very important little rule to remember here. And it is log base b of b equals 1. And here's why. Remember, if we want to simplify this, we just change the exponential. So b to the power 1 equals b. Anything to the power 1 equals itself. So that is precisely the reason that I'm not going to take the common log or the natural log of each side here. I very specifically have to take the log of the base of this particular argument. So 4 is the base here. I'm going to take a log base 4 of each side. All right. Still not simplified yet. We'll use a little bit of properties of logs here. When we have an exponent over here on our argument, we can write that exponent in front of our log. So I have log base 4 of x over 2 equals y times log base 4 of 4. And remember, log base 4 of 4 equals 1. So that has allowed me to get my y by itself, because y times 1 equals y. So it's log base 4, and my argument is x over 2. Now this one not going to be quite as easy to simplify, because we're having to take the log base 4, and they want us to plug in a 4 for the x here, so let's go ahead and do that. So y equals log base 4 of 4 over 2. 4 over 2 is simply 2, so y equals log base 4 of 2. Now, what do we do? I told somebody, I forget who I was talking to last week. It might have been Emily, I'm not sure. All right. Emily or Willie or Devin or somebody in my class had some questions about, how do we do this stuff in the, I was asking them what type of calculator they were using. Sometimes you might contact your instructor and say, hey, how do I enter this? Well, you have to remember there are thousands and thousands and thousands of different calculators out there. And it's always different how you enter the calculator. So we need to simplify log base 4 of, what was it? Log base 4 of 2. All right. So I'm going to show you how to do this on a regular calculator. I mean, one calculator typically we always have in common is we say, hey, we could use our calculator that's on our computer, right? And I know some of you are on Macs and stuff like that, Mrs. Gray. So if you're using a Mac, I don't know, maybe your calculator is different. My wife's got a Mac. I mean, I could go goof around with that calculator, I suppose. I'm assuming the Mac calculator is better than the Windows calculator. I don't know. So first off, if we look at the calculator that comes up on our computer, and this should be the same if you're on Windows XP, Windows 7. I just read some data on Windows 8, and it doesn't look like a lot of people have migrated to Windows 8 yet, but I do have a Windows 8 computer here in the office, but I do not use it very often. So I don't know what the calculator is like. So first thing we're going to do is we're going to go to View, and we have to view the Scientific. By the way, if you want to just curious, so you've got Statistics Calculator, Unit Conversion, Programmer Calculator. You've got actually some pretty powerful calculators that, 35 years ago they would have been very large. Now they're all on your computer. So we need, what is it, log base 4 of 2. All right. Sorry guys, I got to show you one more thing real quick. I guess I need to, before I enter it into the calculator, I need to remind you. I know Mrs. Gray just went over this, but log base 4 of 2, the bases are different, so of course we have to do change of base here. So we need to do log 2 or log 4. Once again, the base 4 was in the base. Always remember that. It helps me remember what goes in the base. All right, so back to our awesome calculator here. So when we use change of base formula, it's log base or log 2 divided by log 4. So this is going to be similar. Yeah, that's a good point. There's a ton of cool calculators online you guys can use too. But the thing that's interesting about this is when you look at all these options that you have over here, you have like x to the power of y, for example. Anything on this particular calculator, and this works the same, I think on a TI-30X, there's a couple pretty popular calculators that it works like this. I have to enter the numerical value that I want the x to be first. So if I wanted 4 to the power of 3, for example, I hit my 4, and then I'm going to hit x to the power of y, and see how it puts 4 in the little caret. But you have to hit the 4 first. So 4 to the power of 3, it equals, and then you're done. So it's similar when we work with the logs here. So I'm going to actually put my log argument in first. So 2, and then I'm going to hit log, because I'm doing log 2 divided by log 4. And then I'm going to use my division bar here, divided by, and don't hit the log yet, hit the argument, and then log. Now this first value that comes up, that's actually what log base 10 of 4 is equal to. So you've got it all entered up here in the top right, you can see, and then you just hit enter, and you get 0.5. So a few different steps there, I understand, but that's how you enter it on there. If anybody's interested, I'm pretty sure on the blog I might have actually using a graphing calculator. It's pretty simple to enter in a graphing calculator. You just hit log whatever the number is and divide it by log whatever the other number is. So that's a little bit easier. All right, so I've got actually run out of time. All right, I had another one for you guys to try that I was going to do, but we are actually over the time limit. I apologize for that. Kind of took a little longer than we expected, so take 5 minutes for me, guys, if you would, though. And I'm pretty sure, let me make sure this is already started up. Just go to the Socrative there for me. And there are some questions on there, that you'll actually answer, but there's not a lot of things that you're going to have to actually work out. So, well, Mrs. Gray, I ran out of time for other different reasons, but